Okay, we are going to talk about how amino acids join up together to form polymers. And of course, those polymers, if they're short, they tend to call them peptides. And when they're a bit longer, you call them proteins. Okay, proteins they can be, I think, the smallest protein, or oxytocin, which we'll talk about in a bit. Oxytocin, which is involved in childbirth and lactation and stuff, that's only 8 amino acids long. But that's very, very short. Most proteins are usually several hundred amino acids long, much longer than that. Okay, so how do amino acids polymerize then? Well, let's have a look at these 2 amino acids here, and what we've got is, get rid of that first. Right, we've got this is alanine, this one here, and this is phenylalanine. These are both on your data sheet, the 6 amino acids they give you on the data sheet. So the R group I've drawn in green. You can see each amino acid has the NH2 group drawn there, and it has the carboxylic acid group drawn there, and it has the so-called alpha carbon there, and that is always asymmetric, that alpha carbon, except in the case of glycine where the R group is an H. Okay, so how do they join up together? Well, it's a condensation polymer, so you lose the water there in the NH2 group and the carboxylic acid group. And if you have a look here, this would be called a dipeptide. This is a dipeptide because there's 2 amino acid residues in it, and this here is now called, this is the peptide linkage. Now, the peptide it's a linkage is a special amide. Okay, it's a type of amide linkage. So it is an amide linkage. But you only call it a peptide linkage when it's between 2 naturally occurring amino acids. So it's that carbonyl group and then the NH group there. Now you probably noticed that with 2 amino acids, so I've got the alanine on the left and the phenylalanine on the right. That can form 2 different dipeptides, because here I've got the alanine as in the so-called N-terminal position. So that because it's the free NH2 group, and here I've got the phenylalanine in the so-called C-terminal position. Now I could quite easily just swap those around, and it would be a different chemical. So if I do that, put the phenylalanine there. So I missed that CH2 there, and just put the alanine there. It's a different chemical, CH3. So I would get used to drawing dipeptides, and they actually say in the specification they might ask you to draw a tripeptide. And when you do that, the best thing to do is to draw your amino acids like I've drawn them up here. So I would put the C-terminal, put the C bit on the right. I would do the alpha carbon in the middle there, and I would do the N-terminal on the left. And the same with this one here. So you've got the N-terminal there. So you're sort of laying them head to tail. Then I would draw a circle around the water that you're going to eliminate, and then join them up together to form the peptide. So I'd have a practice of drawing those. And remember that, yeah, 2 amino acids, you can get 2 possible different dipeptides. Okay, just a little bit more about peptides and a little bit of practice on using skeletal formulae. Actually, I'm just looking at the way the exam board give you the data sheet. That's quite useful there, because they give you the C terminal on the right, the N on the left, and the R group at the bottom there. So you can just, so say if you wanted to do aspartic acid and cysteine, see those two there, you just lay them out like that, and then you could say, right, I'm going to lose the water there, and then join the two together. Okay. Right, now if you look at this structure, first of all, it looks fairly complicated and intimidating, this one here. This is actually aspartame, which is sometimes I think the trade name is NutraSweet, which is in Diet Coke and all those sort of things like that. And it's actually a dipeptide if we have a look at it. So what I'm going to do is, right, let's label the the carboxylic acid. Well, let's draw the basic structure of an amino acid here. So we have a carboxylic acid group, then we have the alpha carbon with the hydrogen attached and the R group, and then we have the NH2 group. Remember that this carbon is always asymmetric, except in the case of glycine, when it's not in glycine because the R group is hydrogen. So, and then this is actually shown. So these asymmetric carbons, can you see with the wedge there? That's one of those alpha carbons. That's another alpha carbon there. Let's draw the C terminal ones with a yellow dot. Well, that's the end. That's the N carbon. Now you can see there it's not a free carboxylic acid. It's actually a methyl ester. So aspartame is not quite a dipeptide. It's a methyl ester of a dipeptide. Slight modification. Okay, and there's another one of those carboxylic acid for the end there. Now we've got a carboxylic acid here, but that is part of an R group. So I think I'll do the R groups in purple. So this is all R group here. That's the R group of that one. See, yeah, it's attached to the alpha carbon, the red one. Where's the R group of this one? Well, it's here. This is phenylalanine. Okay, and we can see which amino acid this is. It's got basically this R group here is so you've got CH2 there, and then you've got another carboxylic acid group. And if you have a look there on this, you'll see that is aspartic acid. There is aspartic acid, so that's what we've got here, and we've got phenylalanine on the right. So you've got aspartame is a dipeptide of aspartic acid here, the N terminus, phenylalanine, the C terminal amino acid, and it's a little bit modified because it is, as you said, it's a methyl ester, and that tastes very sweet. Okay, I've got a much bigger one here. Now this is oxytocin. This is oxytocin. So we use the same, I think we use the same color coding here. So I'll just do it again. So carboxylic acid group, the alpha carbon, the NH2, hydrogen, and the R group. So do that. Alpha carbon we'll do in red. The R group will do in purple. Okay, so let's have a look at this one. Right. Right, so let's see. We can see where the peptide links are as well. So these are the carboxylic acid. Okay, now some of these carboxylic acids are R groups, but these are all part of the peptide backbone. So, okay, there's one there. I'll talk about this cysteine, this sulfur bridge in a minute. Right, now we need to do the alpha carbons in red. The alpha carbons, now you can see got there, and it's asymmetric because it's got the dashed line. Now this alpha carbon, this is glycine, so it's not, it isn't asymmetric. There's an alpha carbon there, one there, one there, one there, one there, there, there. Okay, now we need to color in the R groups. So, right, so the R groups, I think I'll do those in a highlighter, purple. Wrong one. So that can be the R group. So there's an R group. This is an unusual R group, because you can see it actually means that the amines are secondary amine. That's in proline. That's very unusual. That's the only one where the NH, you don't have an NH2 group, you just have an NH group. This is asparagine, an R group, and that contains an amide. You might be able to see there. Here's glutamine, which is another one with which is the R group contains an amide. Isoleucine, that's just hydrocarbons there. This is tyrosine, which is very similar to phenylalanine, except the only difference is that it's got an OH up there on the benzene. So there's the R groups here. Here's the R group. Now here's 2-cysteine, which contain the sulfur as the R group. And right, and there's another R group there. Okay, so again, you wouldn't never be asked to do anything like that in an A level round, just to have a look at it and get used to skeletal form a little bit of practice, but they wouldn't actually ask you to do that, so don't worry if you find that quite difficult. Right, so that's, I think there's eight amino acids in that peptide. It's a very short, as a protein goes, it's a tiny protein. Oxytocin, so involved in childbirth and lactation. Here you can see, we'll talk about this in the next video, here you've got 2 cysteine residues, and what's happened is the 2 SH groups, which I'll draw here, you've got 1 SH group there. So this is one part of the protein, this is another part of the protein. What happens is it gets reduced, you remove these, so you get oxidized, you remove those hydrogens, and you form a covalent bond between the two cysteine residues, between the 2 sulfur atoms, and that holds the protein in a different shape. That's called the disulfide bridge. And that's very common. A lot of proteins have disulfide bridges in them. Okay, so we'll leave that there.